Okay, so yesterday we took a look at direct variation. Oops, slide it down a little bit. And that's in the form of y equals kx, where x and y are variables who are related by a constant k. And our k, we know, is called the constant of proportionality. Because it stays the same, so it's constant, and it gives us the relationship between x and y. All right, so let's look at an example of this one. If we have a rectangle, and we know the formula for a rectangle for the area is equal to length times width. All right. Now suppose we have a rectangle, and our area is 20, and we have a length of 4 and a width of 5. Pretty straightforward. Now suppose we fix our length and we say it's k. So 4 is going to stay locked in place. Every time we adjust 5, then our area is going to adjust by our constant proportionality, our 4. So for example, if I took our width and I extended it out, so we said this was 5, this was 4, and we extend this out another 3 to make our entire rectangle length 8, then this becomes 8 times 4, and that's going to equal 40. Whoops, 32. Mr. Monroe can't do math today. 32. So we see with a direct variation, as our width increased, our area increased by our ratio of 4. Now, that's direct variation. Today we're going to take a look at another form of variation, and that is inverse variation. Now, looking at our same example, we've got our rectangle. So we're going to start out with our rectangle. And we're going to say this is 5 and this is 4. And so we know our area equals 20. Now, instead of fixing, so we have 20 is equal to 4 times 5, let's make k, 20, our constant of proportionality. So no matter what happens, we need our area to remain 20 as a constant. Now, if I were to change my width from 5 to 10, so now I've got 20 is equal to my length, which I don't know yet, times my new width, which is 10. Divide both sides by 10, and I have my new length is 2. But wait a minute. Up here, as one increased, the other increased. But down here, as my width increased, my length decreased. Well, that makes it an inverse variation. And our formula, there's a couple of different ways to write our formula. Okay. Now, our inverse variation formula, we can write it as k equals xy, which is what we just did right here, because we put our k over here on the equal sign opposite our length and our width. But if we want to solve for y, so we get it in the same form as our direct variation, then we can divide both sides by x and rewrite this as y is equal to k over x. So this is the formula we're going to start playing with, our template that we're going to start playing with. Now, if we remember from fractions, in order for inverse variation to work in this form, what can x not equal? X cannot equal 0, because otherwise we're dividing by 0, and when you divide by 0, bad things happen. So we can't divide by 0. Alright. So I'm going to hit pause here and get another example and get everything set up. Okay, let's look at an example. In this case, a word problem. So we have the time t it takes the BHS theater crew to change out the set varies inversely with the number of workers W. If it takes 30 workers 4 hours to switch out the set, how long will it take 24 workers? All right, so we know, because this says inversely, that we are dealing with a y equals k over x type situation. So the first thing we need to do is we need to figure out what k is. So we know that it takes 30 workers 4 hours, so 30 workers, 30 W, and 4 hours T to set up our set. Then we're going to go 4 is equal to k over 30. And then we're just going to multiply both sides by 30. And we get k equals 120. So now that we have this, we have k, we can answer our question of how long it's going to take 24 workers. And that's simply going to be substituting our values in that we have, y equals 120, because that's what k is, over 24, that's what our current number of workers is. And if we divide that out, we get 5 hours. So 30 workers in 4 hours, 24 workers takes 5 hours. So as the number of workers decreased, the amount of time increased, inverse variation. And if we do a table, so we have workers and time, and we already have 2 pieces of our information. I'm just going to do a couple more just to show you how this looks. So we know 30 workers is going to take us 4 hours. 24 workers is going to take us 5 hours. If we go down to 12 workers, that's going to take us 120 divided by 12, 10 hours. Likewise, if we double the number of workers to 60, and we're assuming there's no interference, like 60 workers can work on this without decreasing the efficiency of the process, then this is going to drop down to 2 hours. If I take it to 120 workers, then it's only going to take an hour. And if I were to take it out to 240 workers, then that would only be half an hour. So we can see, if we look here, as these go up, these are going down. Inverse variation. And usually, you can tell, based on the type problem, it will either explicitly say it, or if we have a set where we have our x and y values and not given our k like this, and we're told it's inversely. Usually work problems like this are going to be a inverse variation, where the more workers, the less time. Okay? So, just in recap, we have direct variation, which is y equals kx. So goes up, goes up. Inverse variation, we have y equals k over x. So as x goes up, y goes down, or vice versa. And this form right here is something we're going to start taking a look at tomorrow, where we have the x in the denominator position. This is our first rational equation. And we're going to take a look at those starting tomorrow. I'm sorry, starting Thursday. Tomorrow we're just going to do application of direct and inverse variation. So Thursday we'll start taking a look at rationals.